This video is sponsored by Opera.
The legal power limit for a laser pointer is 5 milliwatts. Well, I think it would be funny to build one that's 50,000 times stronger than that.
Now, I've showcased a lot of ridiculous portable lasers on this channel, but so far, none of them come close to that kind of power.
Even my strongest laser, which was world record breaking when I built it, isn't even half of this level. Now, considering the advances in laser tech since I made this thing, I think it's time to build a laser pointer that just completely blows it out of the water. Now, I'll admit that more power isn't my only motivation here. This laser is horribly designed, and it is just plagued with issues. Not only do I want the next one to be stronger, but I want it to be good and packed with cool features.
Like the last one, the heart of the new laser is going to be the best diode array that the Chinese black market has to offer. The kicker is that there have been 5 years of improvements on these things. The new arrays are stronger, brighter, and more efficient.
They still carry the same dubiously legal charm as the last ones, though, as they still ship with scratched out part numbers, and the manufacturer still denies that they even exist. Now, as long as I can input money into eBay to acquire these, then I'm not going to complain. I mean, honestly, the feeling that I'm not supposed to own these really adds to the appeal.
I've hooked a new array up to a lab power supply as a test, and although I can't push it to full power on this thing, it gives an idea of the insanity that I'll be working with here. The array is the same physical size as my first one, but with more emitters packed in the same area, and according to the sketchy datasheet, it's rated for 161 watts of output power. I'm actually going to attempt to push it far beyond that using some overclocking techniques, but that's going to take more careful design than this piece of trash I built 5 years ago.
Now, if you think I'm exaggerating when I say this thing is poorly designed, well, it randomly quit working a few months ago, and I don't even know why. So let's open it up and see what's going on. Now, it definitely smells crispy under here, but I don't actually see anything that's like burnt up. Well, it looks like it's the batteries. They are completely fried. I wonder if the dead batteries has anything to do with how you have to like smash these batteries into the laser. Like, seriously, they don't really fit in here. You have to like crush the batteries. And like, yeah, if there's one thing that lithium batteries love, it's to get crushed like this. And the worst part is that because I didn't build a charger inside of this thing, you have to, take it apart every time and then crush the batteries again in like a slightly different configuration. Oh man, I'm very happy that this thing never operated in pipe bomb mode. The cooling in this thing sucks too because it's just this giant chunk of aluminum that doesn't have any real connection to the case there, so heat just builds up without anywhere to go. And then these laser drivers kind of suck too. I mean, if I would have used chips from this Century, they would be a lot more efficient than they are here. But you know what really cursed this project from the beginning? The very first sentence of the video.
Hey everybody, it's the year 2020 and I want to celebrate. Now typically on this channel, I like building crazy attractions.
Yeah, that didn't age so well, did it? So this time, I'm not going to celebrate that it's 2025, but instead I'm going to celebrate the fact that my channel has now made it 18 years on this platform without getting banned. And yeah, it's not like I needed a reason to build a bigger laser, but if I'm going to correct the issues from the first video, I might as well be comprehensive.
The one thing I did like about the first laser was the radar gun housing, so I bought another broken one on eBay. I took it apart and pulled out the cool old microwave circuitry, and then added my own control circuits, a charging port, and a bunch of switches. Next, I picked up some batteries, and assembled a pack using a battery management board. This should hopefully reduce the risk of catastrophic failure, or even a boring failure like over-discharge. I needed a circuit to carefully drive the ever-living daylights out of the array. Usually I use an IC from the 70s for this, but in the interest of efficiency and size, I dead-bugged some modern purpose-built ICs for this task. Now I took a risk here, since I built these to far exceed the array's ratings.
This array is rated for 3.5 amps of drive power, so I decided that 4.7 would be a better number. Now yes, this carries the risk of destroying it early. However, with proper cooling, I think it should hold up. This will give up to 255 watts of output power, which obliterates the last one at 100.
I also added a PWM feature to the driver for audio-visual effects. I first tested this feature on a weaker array, and it worked better than I expected. That sound you hear is actually coming from the laser hitting the wood. Now this is where things got difficult. I still had cooling to deal with, and since I didn't want to machine an elaborate heatsink, I figured water cooling would be the better option. I picked up a water block designed for CPUs, along with a pump and radiator, and assembled a cooling loop. However, jamming all the plumbing into the case along with the electronics and batteries turned out to be very difficult. In fact, not long after finishing the laser, the control electronics burnt up randomly, and then when I rebuilt them, they all burnt up again. The circuitry isn't even complicated, but because it was all free-wired, it was incredibly time-consuming to redo. I never actually identified the problem, so when I finally decided to try building it once again, I added all sorts of fail-safes against shorts and voodoo voltage spikes. The third time was the charm though, it seems, as this version survived past initial testing.
I actually want to apologize to all my channel members and Patreon supporters that followed this project, because it took so much longer than I expected. However, as you're about to see, this is the craziest handheld laser on the planet, so I really hope it was worth the wait.
With an output of 250 watts, this laser eclipses the threshold for the highest laser danger rating by a factor of 500. That means that just 0.2% of the laser's power is already considered an instant blindness hazard, as well as a fire hazard. The luminosity of this laser is especially impressive as well, having more than quadruple the brightness of my 100-watt laser, as this one is a brighter sky blue color. It's funny because, even though I built this thing, part of me still finds it hard to believe that a device like this is even possible.
Let me give you a quick rundown of the features of this laser. So this switch right here turns the whole thing on. Then you can see the readouts there for the battery voltage and temperature. Then these switches right here are what turn on the water pump and the cooling fans, which are impressively quiet, I have to say. Then the safety switch is right here, which of course arms the laser. Then these knobs right here control the PWM frequency and duty cycle. But for the time being, I'm just going to leave these maxed out. And then the trigger right here is what finally fires the laser. Pretty cool, right? I'm sure you're wondering, what can you burn with the world's strongest handheld laser? Well, a lot of things. Now, spoiler alert, the real crazy stuff happens when you stick a lens on front and focus the beam to a tiny point. But let me first show you what the unmodified beam is capable of.
Let's start with a block of wood. The beam ignites the wood basically instantly, and you can even hear a little explosion as the pyrolyzed vapors catch fire as well. The small portion of the light that reflects off of the wood is able to illuminate my entire shop. That's a lot of light. Cutting electrical tape is a classic demo for a strong handheld laser. But of course, this laser is well over 1,000 times more powerful than what's needed to accomplish this. The tape is sliced as fast as I can wave the beam across it. The same goes for any sort of thin plastic I throw in front of it. A plastic cup is quite a bit thicker than the tape, but it doesn't seem to have much meaningful effect against the laser. The beam punches straight through it without issue.
While we're doing classic experiments, let's pop some balloons. That was pretty quick.
While we're doing overkill, matches are unsurprisingly no match for the laser. Slow-mo shows that they make it about 0.02 of a second before catching on fire. Newspaper falls in the instant ignition category as well. Just barely clipping the beam is enough to light it on fire. Any paper product is this way really, but paper bags make an especially satisfying sound from the flash pyrolysis. You might think that solder would be a challenge considering how reflective it is, but nope, it melts nearly instantly. A CD was the first real challenge for the laser. Of course, it still caught on fire instantly, but it took a while for the beam to punch all the way through. I think the sooty flame in front was attenuating the beam before it could hit the plastic. The end result was pretty neat though. I briefly talked about the PWM feature, and I want to show you what this does when it comes to burning. By switching the laser at audio frequencies, the target actually makes sound as it vibrates from thermal expansion and contraction. In fact, this effect went far beyond my expectations, and now I'm wondering about the possibility of building a musical laser. I'll have to save that for a different video though. Alright, now it's time to actually test this laser's true destructive power. I'm going to stick a big f-theta lens on front in order to concentrate the output to a point and maximize power density. Everything I've shown so far can be accomplished by weaker lasers, so this is the point where I enter uncharted territory for a handheld laser. Let's start by trying something that the last record breaker couldn't accomplish, melting a penny.
Alrighty, let's try melting through this penny.
It's on fire! What? Oh, that's crazy! I wasn't expecting it to burn.
It burned the zinc inside. That's nuts. Wow.
It's hard to see the actual flame when there's so much blue light from the laser, but I did manage to repeat the effect and get a flame to sustain for a bit after turning it off. And as a bonus, it left a bizarre frozen smoke remnant of zinc oxide. The fact that the laser literally lit a penny on fire is an astonishing result to me. I've done all sorts of mad science experiments with pennies over the years. I've dissolved them in acid, treated them with cyanide, hit them with 1,000 amps, blasted them with other lasers, but none of those methods ever managed to light a penny on fire. Even torching a penny doesn't ignite it, it simply melts it. I think the reason the laser can ignite pennies is due to extreme local heating. The zinc that's being exposed to the laser is likely reaching its boiling point faster than it can transfer heat to the rest of the penny. Then the resultant jet of zinc vapor goes on to ignite on contact with air. At that point, the heat from combustion can sustain the flame for a bit even after the laser is removed. I think that explanation makes sense, at least. For the next experiment, let's see if the laser can make it all the way through an aluminum can.
I'm pretty sure this thing will burn through one side of the can, but to go all the way through, that's what I'm not quite so sure about. But, let's give it a go. Oh, wow, it was just instantly. This thing keeps surprising me. That's insane.
The last record breaker couldn't defeat an aluminum can either, so the increase in power is pretty obvious here. Let's see if the laser can open up this glass soda bottle.
What could possibly go wrong? Oh my gosh! Oh my gosh! Oh, I'm so happy it exploded like that. Oh my gosh. It was like a glass balloon.
That was fun. Let's pop another one for good measure.
Well, it's not exactly an ideal bottle opener there, but that was pretty cool. Now my shop is going to smell like beer, or I mean soda.
I wonder if the laser is strong enough to punch through drywall.
You're kidding me. Wow. It's white. You'd think that it would like reflect off all the light. That's bonkers. I would have never thought that that would be possible with a handheld laser. That is ridiculous. In the early days of big pulse lasers, before there were precise methods of power measurement, lasers were measured in Gillettes. Now, this literally meant how many Gillette razor blades the laser could shoot through in one shot. Now, this kind of measurement doesn't translate to a laser that can operate continuously. But even so, I want to try shooting through some razor blades.
I even found some Gillette blades from the time period of early lasers to try this with.
Alright, moment of truth. Is the laser at least one Gillette? Let's find out. Oh yeah, not even a challenge. That was instantly. In fact, I want to see if I can actually cut this thing in half. Wow. Yep.
Now let's see how fast it can punch through 5 blades in a row.
Alright, here we go. Jeez. That is so wild. Wow, that's terrifying, honestly.
The way to make the Gillette measurement make sense with my laser is to convert it into a rate, essentially going from units of energy to power. Since the laser burned through 5 blades in 0.9 seconds, I can say the laser has a strength of about 5.5 Gillettes per second. Let's try a utility blade that's more than 6 times thicker than the Gillette. No problem there. Considering how fast the laser can melt holes in these razor blades, now I'm going to try welding 2 of them together.
Alright, time to test out if if this thing can weld. I can see it glowing and sparking. That's gonna be a good sign. Well, I melted through. I don't know if I actually welded it, but let's take a look there. Yes, it did. It actually welded it. No way. And look at that. It actually welded that. Now, if anything, I should have moved faster just because where I held it too long, it burned all the way through. But it legitimately is holding that together.
Let's see if the laser can melt through copper wire.
All right, here we go. Oh, it's melting. I think it's gonna work. Yes! Well, there it is. Wow. Well, this thing's really going toe-to-toe with a microwave. I would have never guessed that.
This seems like a stretch, but I'm going to try punching through this piece of titanium here.
Alright, let's see if this works. No way. What? It just shot through instantly. It shot a huge hole through it. Just instantly. That's insane. Now, titanium is not something that just melts easily. And as a demonstration, I have this torch here. So, I can hold this here all day. It's not gonna melt. This one's really surprising to me.
In my last video, I built a 20,000 watt microwave, and in one of the experiments I used it to make ruby. However, the setup was far from ideal. It was impossible to concentrate the energy, and my containers kept exploding. Thus, the rubies I did manage to make were pretty small. I'm going to see if the laser can do it better. The starting mix is the same as last time. Alumina powder with a couple percent chromia added, which I got from Nighthawk and Light's video on cooking up rubies in a home microwave oven.
Yeah, don't ask me about the name on that one. Alright, let's try cooking some ruby. Now it's sparking. I don't know if it's actually... Oh, it's so hot. It's just glowing so brightly through these goggles. Oh wow, that is so hot. Oh my gosh. I had no idea it was like just melting it so well. It's crazy. I think I just made a huge ruby too. No way. I can't believe it's gonna work this well. This laser just keeps surprising me. Oh, it melted like a big old glob. I think it like beat the daylights out of the microwave actually. I had no idea that it was cooking that well. And look, it just made an enormous, huge ruby. What? That's crazy. It's huge. What? It just made this giant ruby. That is crazy. In fact, I'm going to go ahead and give this guy a pluck. Oh my gosh, it's an enormous, enormous ruby there. I'll clean that off and make another one here quick.
This turned out to be a really reliable method to make big rubies, and it blows the performance of the microwave out of the water. Even freehanding the laser produced bigger rubies than I was able to get via the microwave. I'm very impressed with the size of these. I've never offered merch before, but I don't think anything could beat laser-grown ruby as my first product, so I made a few extra to offer my viewers. Check the link if you're interested. I'm curious whether white sand is reflective enough to resist melting in the laser beam.
Oh yeah, just instantly melting. Oh my gosh, it's so bright. Even through these goggles. Oh yeah. Wow, look at that stuff glow. And it's white too, like you'd expect it to just reflect it all away, but nope. It just melts straight through it. That's just bonkers, man.
Considering how well everything else has worked, I'm going to try zapping tungsten wire. Now, as a reminder, tungsten has the highest melting point of the metallic elements.
This is crazy that I'm even going to try this one. Oh my gosh. Oh, it's so close. I don't know, man. I'm gonna have to get the focus better. Oh, it was close, but I think it was slightly out of focus. So I'm gonna move this back just slightly and try it again. All right, I think I have it lined up better this time. Oh. Yes, it worked. Oh my gosh, I cannot believe that. That is insane. I would have never expected this laser to go like toe to toe with a microwave. My goodness. That's crazy. That is crazy.
The wire burned here instead of melted, but even so, that still takes some incredible temperatures. The only other extreme material I can think to test the laser against is diamond, so I picked up some synthetic diamonds to laze. I honestly don't know what to expect from these.
So by some chance, can this thing burn through diamonds? Let's find out. Oh, they're burning. They are absolutely burning there. Oh, I think one just exploded. Wow. It actually lit a diamond on fire. Wow. That's amazing.
I guess it shouldn't be so surprising that diamonds burn, considering they're just carbon, but it still takes a very hot temperature to ignite them, and they reflect a large portion of the laser light anyway. In fact, the diamond reflections are particularly scary, since the crystals reflect intact portions of the beam and result in a terrifying disco ball of insta-blindness. My goggles protect my eyes just fine, but I'm glad none of the beamlets hit my cameras, as I'd hate to destroy all my cameras again.
Oh, that's interesting how it changed allotropes there. It turned to amorphous carbon there in the center, and you can still see some, unlazed diamonds there on the side. Oh, that's weird. That must have got really hot. I could see some of them burning too. I could see the sparks flying out. But yeah, it changed the allotrope.
Lithium coin cells aren't exactly as tough as diamonds, but they turned out to be a lot of fun to zap. Their metallic lithium content makes them quite pyrotechnic when they fail.
Heck.
Interestingly, the effect depends on which side is hit by the laser. Blazing the positive side is what gives a rocket-like effect, with flames colored red from lithium's atomic emission spectrum. Hitting the negative side is what makes them pop more violently.
Heck. Oh, there's lithium burning on there. Oh boy.
One of the batteries even splattered some molten lithium on the laser lens. Oopsies.
So I have an old style ping pong ball here. Now these old style ones are flammable because they're made out of nitrous cellulose. But the problem is it's hard to find those locally, so I have to order them online. But because I've bought these online, now I get sent this physical spam in the mail from Paddle Palace. It just sounds so bad. But I don't play ping pong ball. All I do is just blow these things up with lasers. So anyway, I'm going to shoot through one with this huge laser here. And yeet. Yeah, just instantly. Typically, when I make videos about my lasers, I show you all the cool stuff that they can do and leave out what they can't. But some of the failures are even more interesting. So, what are some surprising things that this laser struggles with?
Burning a hole in a CD case is a classic demo for a powerful handheld laser. Going back to the archives, it shows that a 1-watt laser takes a few seconds to pull this off. So, does this laser do it 250 times faster? Nope, it's actually slower. What's going on? Sometimes there's a paradoxical effect with lasers, where increasing the power weakens its effects on materials. Flames, smoke, or even plasma from the laser hitting the target can absorb most of the laser light and protect the material beneath it. This effect is very prominent with pulsed lasers, and explains why this laser can pop craters into tungsten, even though it struggles to pop a balloon. The CD case immediately shot a jet of sooty fire when it was hit, and I think that played some protective effect. I've also noticed that some materials can become self-healing to an extent when more power is applied. For example, my laser welding system actually cuts steel faster with the power turned down. At full power, even when the beam does punch through, the hole tends to immediately close back up when the laser is turned off. The reasoning is that the higher power results in more molten material that can fill in gaps. I tried another CD case at roughly 10% power using the PWM feature. Sure enough, it burned through faster with less power. I then tried it at full power, but slightly out of the focal point to lower the power density. Since it didn't catch on fire, the laser shot through almost immediately.
I always say that most problems in life can be solved with very powerful lasers. And although this may seem like an exception, the reality is that the problem will go away if you throw even more power at it. The issue is that more power isn't always possible, at least based on engineering constraints or even the current state of technology.
Mirrors also showed some self-healing effect. Ironically, it was the shiny part that burned, while the glass simply melted and prevented total burn-through.
Another surprisingly difficult task for the laser is igniting flammable liquids. For example, I've got this glass of butane here, and oh, look how angry that is. They're just like boiling away. Just the tiniest little spark is all it takes to turn this thing into a fireball. So, what happens if I shine the laser at it?
Absolutely nothing. The thing about flammable liquids is that it's really their vapors that ignite. It's easy to imagine a laser as just a long-distance torch, but unlike a flame, the energy from a laser has to be converted to heat via absorption by a material. The problem with vapors is since they're transparent, they don't absorb light and thus they don't heat up. You can get around this with a laser many thousands of times more powerful, as at that point you can initiate a spark via the electric field. But for a laser like this, I have to cheat and add something else to burn that can then go on to ignite the liquid. I figured that the plastic case of a lighter would provide enough flame to ignite the vapors released when it pops, but even this turned out to be a challenge.
Are you serious?
I eventually got one to go up in a nice fireball though.
Oh my gosh!
I did find that with this laser, I can just pour a flammable liquid on the floor and then ignite it by pointing the focused laser at it. I'm still cheating by heating the concrete to super high temperatures, but still my first handheld laser that can at least do this. It's crazy just how much power it takes to get to this point. What about snow and ice? One of my most common suggestions is to make a laser that can quickly melt snow off of driveways and sidewalks. But unfortunately, lasers suck at this. Snow is highly reflective, so most of the light bounces off instead of heating and melting it. The bigger reason, though, is that ice takes an enormous amount of energy to melt. Water is incredibly stubborn thermally, and in order to get it to change phases or even temperature, you have to dump in a ton of energy. My much bigger and stronger laser welder can slice through about anything, but when it comes to snow and ice, it hardly makes a dent. Yes, that's running at the full 2,000 watts there, yet its effect on the snow is barely noticeable. The full power only becomes apparent when I hit something other than snow with it. In fact, this laser will melt steel faster than ice of the same thickness. Funny how that works. Assuming perfect 100% light absorption and ice right at the melting point, my handheld blue laser could, in theory, melt 0.75 grams of ice per second, or basically 1 ice cube per minute. This is a great example of how lasers aren't impressive for their raw power, but instead excel in power density.
Since I'm claiming that this is the most powerful handheld laser in the world, I need to make some clarifications. So by handheld, I mean something that can be, comfortably held in one hand and also has its own enclosed power source.
So an example of something that wouldn't count towards this would be my laser bazooka. It's portable, but way too big to be considered a handheld. It also sucks. Another example would be my laser welding and cleaning machine. Yeah, the output is fed through a handle, but it's tethered to a 400-pound machine that doesn't even have its own power source. So no, that's not handheld either.
Another important distinction when I'm talking about the most powerful laser is I'm referring to CW, or continuous operation. Pulse lasers can achieve far higher peak powers, but only for a tiny fraction of a second, and in general, they're much less destructive than CW lasers.
For example, this laser I built nearly a decade ago achieves higher peak powers than what I showed in this video, but only for billionths of a second. Overall, it's a much weaker laser.
Now, funny story, I was actually contacted by a very large record book company about the original record breaker, but I didn't pursue it because it involved having the power verified by 2 independent sources. Now, don't get me wrong, this is a very reasonable expectation, but it's actually kind of hard to pull off. So a laser power meter that can measure hundreds of watts is expensive, and it's just not something that's like commonly encountered. So only a few companies and universities are going to have something like that. But the bigger issue is that most people that work with big lasers for their career aren't going to want to be near lasers like this. Like, it's easy for me to get desensitized to this kind of stuff, but no, this is a psychotic project. And I can only imagine the aneurysms that OSHA and lab safety would have over these things. And even if I did find 2 people willing to test this laser for me, it's not like I can ship it or take it on a plane with me. It would have to be within driving distance. And because where I live isn't exactly the mecca of photonics, looks like you're probably just going to have to take my word for it for the time being. Earlier I said that this thing is 50,000 times over the legal limit for a laser pointer. So, does that mean I'm going to jail for making it? Nope. So the cool thing about US laser law is that limit only applies to the sale and import. So there's nothing stopping me from making death rays in the comfort of my own home. Now, of course, I can't go out and sell this thing or play with it in a park, but I can show it off on a YouTube video.
One additional point I should add is that the US laser pointer limit of 5 milliwatts is actually quite lax compared to the rest of the world. Canada, Australia, and most of Europe set the limit to 1 milliwatt. So if you're in one of those places, my laser is actually 250,000 times stronger than anything you can buy. Now personally, I think 1 milliwatt is too restrictive, since that's hard to see in a well-lit room. Besides, even at 5 milliwatts, the data shows that our blink reflex is fast enough to prevent eye damage from a direct hit.
One final point I want to cover is safety. So my more recent videos have dealt with projects so extreme that I haven't even bothered with the whole don't try this at home bit, just because honestly, this kind of stuff is beyond what can be replicated without specialized tools or equipment. And yes, this laser is so far off the laser danger rating scale that its eye hazards are incomprehensible. However, that's not what I want to talk about with this bit. I want to talk about handheld lasers that you can buy online.
If you have a laser that looks like any of these, chances are that it's quite a bit over the legal power limit and can cause permanent eye damage from even an indirect reflection. A laser doesn't have to be record-breaking to obliterate your retinas if misused. I realize this warning may seem ironic coming from me, but laser eye injuries are unfortunately very common today. I've covered this topic more in depth in some previous videos, but the gist is, tread very carefully with lasers bought online.
Now I have to say, I'm glad to finally finish this project and put it behind me because it felt like every single part just took way longer than expected. So a big thank you to all my channel members and Patreon supporters for sticking it out, and really for making projects like this possible. And I also want to give a big thank you to Opera for sponsoring this video. I've been using Opera for a while now, and it's the fastest browser I've ever used. On the surface, it simply loads pages quickly. Where it stands out is in its time-saving and productivity-enhancing features.
For example, my favorite feature is tab islands. It's crazy how quickly a browsing sesh can lead to 30 open tabs, and tab islands make it easy to revisit those tabs by grouping them by topic. I find this to be super useful when researching for my projects, since they neatly expand and collapse. Plus, tab traces make it even easier to find my most recently visited tabs, thanks to a subtle underline. The more recent the tab, the darker the underline. I also love the split screen feature because it allows me to open 2 pages in the same window. This is useful for all sorts of scenarios, like cross-referencing schematics, fact-checking articles, and comparing videos. It simply activates by dragging the tab down. The sidebar is great because it allows me to quickly access my various socials, and in particular, it also contains an in-browser player. I can listen to music on 6 different streaming services without interrupting my browsing, since pausing or skipping a song is as easy as hovering over the player button. I can even detach the player and move it anywhere, including outside the browser window. Opera allows me to customize my entire browsing experience with dynamic themes. These go beyond a simple light or dark mode by tailoring my browser to fit my mood. The integrated AI Aria is super useful as well. I can instantly bring up the command line with a shortcut, and then have it summarize pages, generate and interpret images, and answer questions I have.
So yeah, if you're wanting a faster, more productive, and customizable browser, you should give Opera a try and click the link in the description.
Thank you again to Opera for sponsoring this video. Well, until the next time, stay safe and happy lazing.